A uniform thin rod of length L and mass M is fixed at one end, and the other end is allowed to fall from this position down to here, and the rotational inertia of the rod about at the end point is I is equal to ml squared over 3, which you could look up in one of those charts. It's 1/3 ml squared. Part A, derive the expression for the linear velocity, that is the v of the free end of the rod. So the whole rod is moving with an angular velocity, omega, but the very end of the rod, you could say that that has a linear velocity of v, which is what we're trying to find. And we're going to do this using conservation of energy. So when the rod is held horizontally, it is at the highest point, and then as it swings down, it's turning that gravitational energy into kinetic energy. But since the rod is fixed in place, it cannot translate, it can only rotate. So to set up the conservation of energy equation, it's going to look like U initial, the gravitational energy, is equal to K final, the kinetic energy, that's rotational kinetic energy, so this would be mgh is equal to 1/2 I omega squared. So the h right here is the only thing that may be a bit of an issue, and that's why there's the hints for this problem, that since this end of the rod doesn't change in height at all, but this end of the rod changes in height by a distance of L, the length of the rod, because from here down to basically level with that point is the height is L. The whole rod has a different change in height depending on what part you're looking at. So we just consider the center of mass of the rod. From this point right here to this point right here, that height is basically half the length of the rod, or L over 2. So that's what I'm going to plug in for the h right here. So I'm going to put in m g L over 2 is equal to 1/2 times I, which was given as m L squared over 3, and then times that omega squared from right here. Let's cancel a few things out on both sides of the equation. We have a 2 in the denominator, which I'll cancel out. We have an m that I'll cancel out. And technically, you could also cancel out this L with one of these L's. What I'll actually recommend against doing that for right now, because this V down here, remember V is equal to, for rotating objects, is equal to R times omega. And in this case, the R, the distance from here to the rotation point right there, is that distance L. So V is equal to L times omega. So by leaving this squared on the L, I can take this whole thing here, this L squared omega squared, and say that L squared omega squared is equal to V squared. Since V was the ultimate thing I'm looking for, if I replace all of this with a V squared, I'll be able to find that a little bit easier. So I have GL is equal to V squared over 3, and then just multiply both sides by 3 and take the square root, and you get the V, the linear speed of the bottom of the rod, is 3GL. The rest of this problem is a linearization problem, so I'm not really going to do much of it for you because you really should know how to do this stuff at this point, but I will get you started in case you're still having trouble with these kind of questions. You want to plot certain variables so that you can find a numerical value for the acceleration of gravity, the g, using this equation that you just derived. So if you take that equation, v equals the square root of 3gl, and line it up with the equation for a straight line, y equals mx plus b. Well, there's no pluses in that first equation, so we can just say that b is equal to 0, which means one way we can do this is on the y-axis, you can plot the v, that's the horizontal axis, the vertical axis, you're plotting the v in meters per second. On the x-axis, you're plotting the square root of L, since the L is under a square root sign, which would have units of square root of meters. And in that case, when you find the slope of the graph, the slope of that graph would equal to the square root of 3g. Another way you could do this, and this kind of goes back to that pendulum question in the last test, is that you could square both sides of the equation, the original equation, so you have v squared is equal to 3gl, and then when you match this equation with y equals mx plus b, you still have a b of 0, but now on the y-axis you would plot v squared, that's in units of meters squared per second squared, and then on the x-axis you would just plot the length in units of meters, and now the slope of this graph is equal to just 3g, not the square root of 3g. So pick either one of those techniques. If you use the first technique, you're going to have one additional row in the table because the v stays the same, but the L, you have to take the square root of all the lengths, so you would need one row in the table to take the square root of those lengths. Or if you use the second technique, the L stays the same, but you would need one additional row in the table to square all of the velocities. And then when you plot the points on the graph, either the v versus the square root of L, or the v squared versus the L, when you plot those points on the graph, they should all form a pretty straight line. So you're going to do a best fit line on the graph. Remember, that's the line that needs to pass kind of between all the points. You don't want to connect them, just draw a straight line that passes between everything. And then into part D, make sure you label the axes of the graphs and put the units on those axes. You don't want to lose the points for something stupid like that. In part D, that's where you're going to determine the experimental value for G. Now, don't just go in there thinking like, well, I know G is equal to 9.8, so I'm going to get an answer pretty close to 9.8, because sometimes they'll design a problem so that it has like a lot of air resistance or something that you don't know about, and the true value that you get from the graph will come out lower than G, for example. Like in this case, when you actually do the work to find the value for G, you're going to see that it comes out to like 8 point something rather than 9 point something. So you take the slope of the graph. Remember, the way you find the slope, you pick 2 points that are on the line that are not data points, and pick them far apart. So just pick like a random point somewhere down here, just draw an open circle there, pick a random point somewhere up here, draw an open circle right there, and then calculate the slope of that line by doing the change in the y over the change in the x. Once you've got that slope, depending on which of these two things you use, the slope will either be equal to the square root of 3g, or the slope will be equal to 3g. So just take that numerical value, set it equal to either the square root of 3g or 3g, solve for g, and if everything was done right, you're probably going to get a value of somewhere around in the low to mid 8s. I'd say between 8.0 and like 8.7-ish for the ideal graph. Now, if you're a little bit above or below that, it's fine. You may get an answer like in the upper 7s or the low 9s. That's all right. It's just based on the numbers they gave. The ideal solution is somewhere in this range.